Hello and welcome. My name is Nordamia Bintashaniza. Today I will present a summary of a research article titled Experimental Study of the Thermodynamic Properties of High Thermal Conductivity Energy Pi, published in the Journal of Building Engineering in 2023. So for introduction, tell that energy consumption is rising rapidly, especially in China. This raises concern about energy waste and environmental sustainability. One promising solution is the use of shallow geothermal energy, which is stable, renewable, and suitable for ground sources heat pump system. Among these systems, energy pipes are a unique innovation that combines structural foundation support and underground heat exchange. Energy pipes not only support building but also regulate indoor temperature by circulating fluid through embedded heat exchange pipe. However, traditional energy pipes have limited heat transfer performance. To improve this, researchers are now studying high thermal conductivity material, including concentrate at hand with graphite and steel fiber. Problem statement. Most studies on energy pipe focus on ordinary concentrate pipe in dry sand or clay, but real-world application often involve saturated sand, where heat transfer and mechanical behavior can be quite different. Additionally, there is limited research on how thermocycling, that is repeated heating and cooling, affect stress, soil pressure, and displacement in energy pipe. The study addresses that gap by investigating high thermal conductivity energy by under thermocycling conditions in saturated sand. The main objectives of the study were, first, to prepare a high thermal conductivity concrete by 84% graphite and 0.6% steel fiber. Second, to evaluate the mechanical and thermal properties of the concrete compared to ordinary seed-to-peak concrete. And third, to investigate how temperature, stress, soil pressure, and pipe displacement change during three thermal cycles, both with and without load. Let's move on to the methodology of our study, which is centered around a model task. The first step involved the preparation of high thermal conductivity concrete. This is crucial because the material used directly affect the fraction of heat transfer in energy pipes. Next, we examine the properties of the pipe and the soil. They help us to understand how different soil conditions interact with the pipe material, especially under thermal loads. The third part is setting up the model tank and instrument. The setup stimulates the real conditions and allow us to monitor temperature changes, soil behavior, and other important parameters. Lastly, we carry out the test program where all components come together. The actual testing phase provides the data we need for analysis and evaluation. In summary, this structured approach ensures that we can accurately assess the performance of the energy pipe system under controlled conditions. Despite of the methodology, we focus on the preparation of high thermal conductivity concrete. As shown in the table above, the mixed design remains consistent in terms of water, cement, and aggregates, but varies in the amount of graphite and steel fiber added. These additives are important because they help improve the thermal conductivity of the concrete. The concrete used had a strength rate of C30 and a sand ratio of 0.36. To measure its thermal conductivity, we use a CDDR3030B device, testing it over a temperature range of 10 to 70 degrees Celsius. Additionally, we tested the compressive and flexural strength at room temperature. These tests were conducted using the JAS 2000A pressure testing machine and the WEW600B hydraulic universal testing machine. As shown in the photo below, this step ensures the concrete used in the model test meet both mechanical and thermal performance requirements. This slide shows the performance test result of the high thermal conductivity concrete. Starting from the first graph, we can see that as the steel fiber content increases, the thermal conductivity also increases. This effect is more noticeable at higher graphite percentage, especially at 4%. In the second graph, we observe that the compressive strength improved significantly with the addition of more steel fiber and higher graphite content. The best result is achieved with 4% graphite and 0.6% steel fiber. The third graph presents the flexural strength test. Similar to the other result, both graphite and steel fiber contribute to better performance. The combination of higher percentage lead to the strongest outcome. Overall, the concrete prepared in this study achieved 30% higher thermal conductivity compared to conventional C30 concrete. In addition, the compressive strength was 11 higher and flexural strength was 9% higher. Because of this improved mechanical and the thermal properties, this special concrete was chosen as the pipe-forming material for further investigation in our model test. Alright, now let's dive into section 2, properties of the pipe and soil. In this experiment, a modern energy pipe was used. It measured 500mm in length and 84mm in diameter. The pipe was built using high thermal conductivity concrete. perfect for improving heat transfer for performance. To strengthen the pipe, a steel reformer cage was added, which remains T-bar along with 4mm steel stirrups and spacers every 100mm. You can see in the diagram on the left that the pipe include U-shaped heat exchange pipes, arranged with the pipe cross-section. For the foundation, they use saturated sand with an average grain size of 0.96mm based on Bala-Chowsky finding. If the ratio of the pipe diameter to the grain size is over 200, the grain size effect becomes insignificant. Since the ratio in this case was 250, any influence from the grain size could be safely ignored. Now at the bottom of the slide, table to list the key physical properties of the energy pipe, which is length 500mm, diameter 84mm, density around 2400.2 kg per cubic meter, elastic modulus 29 GPa, and thermal conductivity 1.8 watt per meter Kelvin. This value confirms that the model is well suited for simulating real-world energy pipe behavior, both in terms of structure and heat performance. So for this pipe, we used a model tank 600mm wide and 600mm tall, made from 3mm thick acrylic. So to reduce outside temperature effect, we added heat insulation counter inside. The tank size was 6 times the pipe diameter and the gap below the pipe was 0.4 times its length. 3 temperature sensors were set at each layer on the surface at 1 time the pipe diameter and at 2 times the pipe diameter. Next, I will explain the model tank and instrumentation used in this experiment setup. A loading platform was placed on top of the pipe to stimulate loading condition. To monitor displacement, 2 dye indicators were installed, one of the platform and one of the soil surface. To maintain a controlled temperature, water was heated to 60 degrees Celsius using a thermostat water pump. The water pump operated at a flow rate of 22 liters per minute to circulate the hot water through the system. Figure 5 on this slide shows the detailed setup layout including the heat exchange pipe, data acquisition instrument, and sensor position in the saturated sand. Additionally, Table 3 summarizes the measurement parameter, instrument type, scale range, and their accuracies. These include instruments for measuring thermal conductivity, temperature, pipe strain, and soil pressure. Overall, this experimental arrangement ensures accurate measurement and control of all variables involved in this study. In this test, we measured the ultimate bearing capacity of a single pipe, which was 1.2 kN. A working load of 0.6 kN was applied. The pipe was put through a thermocircle. It was heated at 60 degrees Celsius for 11 hours, then left unheated for 30 hours. This process was repeated for 2 more cycles. Throughout the test, we analyzed the thermodynamic behavior of the high thermal conductivity energy pipe. More detail about the test setup can be found in table 4. For this part, result and analysis. A. Temperature field distribution of the pipe and soil. B. Variation of the additional stress of the pipe. C. Variation of the soil pressure at the pipe end. D. Variation of the displacement of the pipe top. Temperature field distribution. During the first thermocircle, both the pipe and the surrounding soil temperature rose quickly within the first 4 hours, then stabilized. The pipe temperature decreased with deep measuring 35.7 degrees Celsius at the top and only 27.9 degrees at the bottom. Compared to an ordinary concrete pipe, the high thermal conductivity pipe show lower internal temperature, pipe transfer more heat to the surrounding soil. This demonstrates the enhanced pipe spread heat more efficiently, reducing internal heat accumulation. Additional stress in the pipe. Due to thermal expansion and contraction, the pipe experienced internal stress during the thermal cycle. The stress was highest in the middle of the pipe and lower at both ends. Under load, the maximum tensile stress reached 0.48 MPa and compressive stress reached negative 0.58 MPa after the third cycle. This value were higher than under no load condition. Also, stress increased with each cycle, indicating residual thermal stress accumulation. This is critical for long-term structural safety. Let's take a look at how soil pressure at the pipe end changes as temperature changes. When the pipe heats up or cools down, its shape slightly changes, and this affects the soil pressure at the very bottom. Without any load applied, the pressure ranged around 32, 30, and 29 kPa. But when a load was applied, the pressure increased slightly to around 34, 31, and 30 kPa. Why does this happen? Well, the side of the pipe can hold too much pressure, so a lot of it is transferred to the bottom. That's why we observe higher soil pressure at the pipe end, especially under load. Also, after going through more heating cycle, the soil becomes less pressure at the bottom. This is because heat causes thermal consolidation. where the saw gets tighter and more compact over time. But then, something interesting happened. As the pipe settles slowly, the bottom pressure starts to rise again. The two graphs at the bottom show this clearly. The left one shows data with no load, and the right one shows data under load. You can see how soil pressure changes with temperature, from the starting point to the finishing point. On this slide, we look at the variation of the displacement of the pipe top during thermal cycle. As shown in the graph on the left, the pipe top moves both up and down as it experiences heating and cooling. Without an applied load, the maximum output movement of the pipe top reaches about 0.19, 0.2, and 0.21 mm. However, once the heating process stops, the pipe tends to move downward with displacement of approximately 0.01, 0.02, and 0.025 mm. When the number of heat cycles increases, the pipe top tends to move upward more significant at the end of the cooling phase. On the other hand, when a load is applied, the downward movement becomes more noticeable, reaching around 0.05, 0.06, and 0.07 mm. Here, the output movement is smaller because the pipe is held down by the load pressure. Additionally, more heating and cooling cycles lead to the greater settlement of the pipe in the downward direction. Both the temperature changes and applied weight significantly affect how much the pipe will settle over time. This information is very important to keep in mind when designing energy pipe to ensure their long-term performance and solution. The study showed that concrete with 4% graphite and 0.6% steel fiber significantly improved thermal conductivity by 30%, compressive strength by 11%, and flexure strength by 9% compared to ordinary concrete. The enhanced energy pipe also showed more effective heat transfer, but it also experienced residual stress, changes of pressure, and pipe settlement under thermal cycling. These factors are crucial for designing safe and efficient energy pipe with rear engineering project. Designer must consider this effect of thermal cycling over time, especially under building load. So, thank you for watching my presentation. I hope this summary has helped you understand the thermodynamic behavior of high thermal conductivity energy pipe. Bye-bye.